Okay, I want to introduce Turan Birol Hoca from University of Minnesota, and today he's gonna present us. The title is First Principle Calculations in Correlated Materials, and correlated materials are nowadays very hot topic, and I will listen to you with curiosity.
Well, thank you very much for the nice introduction, and I would like to also thank the organizers for inviting me and giving me the opportunity to talk a bit about my research here. So my name is Turan Birol. I'm an assistant professor at the University of Minnesota, and my department has a non-standard title, as you might see. I'm in the Department of Chemical Engineering and Material Science. But can you see my screen, or are you seeing my? Yeah, okay, sorry, I shared the wrong screen.
You're seeing your email.
Yeah, okay, by this time, after this much online teaching, I should be.
Yeah, that's okay.
Yeah, okay. This was a nice introduction for a computational physicist, I guess. So, anyway, what I do is I'm a condensed matter physicist. I work on solid state systems, and this is why I'm currently in a material science department. And I know this is a quantum optics conference rather than a solid state physics or condensed matter physics conference. So what I will try to do is I will try to give you a more big picture, a more general introduction to my research area. And in particular, I'm going to start with the problem, which is the problem of electrons in a crystal. And I will tell you about this more well-known method, density functional theory. And after discussing what density functional theory can do and show you some examples, I will tell you about a slightly more fancy computational approach, the so-called dynamical mean field theory approach, which actually captures some of the physics that DFT cannot capture. And then I'm going to conclude with a summary, if there's enough time left, of course. Okay, so the problem I'm interested in is the problem of electrons in a crystal. So we have a periodic arrangement of atoms, nice long-range order in real space. These atoms are held together by chemical bonds. You know, these are the things that we have learned in high school, like ionic bonds, covalent bonds, and so on. And in the end, it's the electrons which determine the macroscopic properties of the material. It's electrons that make these covalent and ionic bonds. So it's electrons that actually hold the atoms together, but also any other macroscopic property, like whether you have a metal or a semiconductor or a transparent material or an opaque material, for example, are all determined by the behavior of the electrons in the solid. So it is extremely important to understand what the electrons are doing there, not only to understand what's these macroscopic properties, which is of course interesting for all sorts of engineering applications, but also because since the electronic Hamiltonians are typically more complicated than what you get in free space in a solid, there is very rich emergent physics that we come across in the solids. So there's magnetism, superconductivity, various topological properties that can emerge in seemingly simple solids, seemingly simple crystals. And sure, so this is an interesting problem. We want to understand what the electrons can and do in a solid. And for just about a century or so, we know that the electrons obey the rules of quantum mechanics. So in order to understand the electrons and hence the material's properties, all we need to do is to solve the quantum mechanical problem. And the quantum mechanical problem, you know, barring some relativistic corrections and so on, really boils down to this, the many-body Schrodinger equation. So this is not a particularly beautiful equation, I would say, but it's just one single equation, and we know what each and every one of these terms are really well. So for the past century or so, people have been trying to solve this equation, just the Schrodinger equation, in the solids for a collection of electrons. Now, it turns out that despite the expectation in the 1920s that once we have the many-body Schrodinger equation, we know everything about chemistry now, one cannot solve for this equation to solve for this many-body electronic wave function psi in this equation. And the reason is what we sometimes call the one flag catastrophe, and it's that many-body physics scales exponentially. So both the computation time to get an answer to this equation numerically increases exponentially, But also, if you consider this electronic wave function, for n electrons, this is a complex function of 3n variables, and you can make a back-of-the-envelope estimate and see that even for a simple molecule, like just say a water molecule with 18 electrons, the electronic wave function becomes too large to store in a classical computer unless you do some big approximations or use a smart trick. And the most common trick nowadays people use is using the electron density instead of the electronic wave function. And this is the basis of the density functional theory. So this trick, usually people cite these Kohn-Sham and Hohenberg-Kohn papers for this idea, but the idea itself actually goes back to the time of Fermi. So this has been an idea that has been around for quite a while. So I'm not going to give you the full derivation of the density functional theory and the Kohn-Sham formalism, but the basic idea is that instead of the electronic wave function, you use the electronic density as the fundamental variable, and you map the system to an auxiliary system, the so-called Kohn-Sham system, Kohn-Sham Hamiltonian, and show that the properties of the Kohn-Sham system and the Kohn-Sham quasiparticles do correspond to certain properties of the real electronic system and the properties of the real electrons in your system. Now, the advantage of this approach is that this auxiliary Hamiltonian, the Kohn-Sham Hamiltonian, is a non-interacting Hamiltonian, in the sense that the electron-electron interaction is not explicitly there in the Hamiltonian, so that you can actually solve for the wave functions of the electrons one by one. So the entanglement is not as much of an issue. And the cost you pay is that, one, this approach is valid only for the ground state properties, which is still great, which is still good for most things that we're interested in. But two, there is about a 1–2% of the energy that we need to approximate, that we don't know how to treat. And it's the part that comes from this term, the so-called exchange correlation functional, the exchange correlation energy. And essentially, this is where we concentrate all our ignorance about the many-body physics of the electronic system. Now, we don't have a closed form for this exchange correlation functional. If there was, like, life would have been much nicer, I guess. But what we do often instead is we use a simpler problem, get the value of the exchange correlation energy in that simpler problem, and assume that in the real material, the exchange correlation energy has the same value. So the simplest problem when you are talking about electrons is the problem of a homogeneous electron gas. The energy of a homogeneous electron gas as a function of density can be calculated numerically exactly, and this is done using the technologies of 1980s, early 1980s. And you can use this system's exchange correlation energy to approximate the real materials one. This gives you the well-known LDA, the local density approximation. One can take one step further and take into account the first derivatives of the electron density as well. And this gives rise to the so-called generalized gradient approximations. So these GGAs, generalized gradient approximations, do lead to some quantitative corrections. And there are people who dedicate their lives in finding better GGAs, and I appreciate all these efforts. But at a conceptual level, this is just a quantitative correction. This doesn't lead to a qualitative change in most cases compared to LDA. But if you want a real change, then you can use a more complicated model like Anderson impurity model to approach this exchange correlation problem. And I will come back to this in the second half of the talk. Okay, now I will show you two examples of what DFT can do. And say the first example that I like, because I worked a lot on this back in my PhD, is the problem of ferroelectricity. So there are many crystals, which are ionic crystals, like say table salts, where you have oppositely charged ions, say sodium and chlorine ions, that are arranged in a crystal with equal distance between them. And these are the materials that give rise to the typical dielectric behavior that we observe. But then in certain materials that we call ferroelectric materials, below a certain transition temperature, the cations and anions are displaced against each other spontaneously. And this gives rise to a small dipole moment in every unit cell of the crystal. And these dipole moments in turn give rise to a macroscopic polarization, a macroscopic electric dipole moment per unit cell, per volume in the crystal. Now, if you consider the Landau free energy, a dielectric looks like this. So there is a single parabola with the minimum of the free energy at zero polarization. But in a ferroelectric, instead, you have this double well potential, and the system spontaneously at low temperature goes down to one of the two minima at a non-zero value of polarization. Now, ferroelectricity is interesting for various applications that I'm not getting into. You can imagine that you can, yes, build a memory element using this. So there's something called a ferroelectric random access memory, for example. But also in terms of the phase transitions, these are interesting systems to study because, well, they usually obey mean field really well due to the long-range nature of the Coulomb interaction, but also the symmetry of the materials can be really rich. So this ferroelectricity is ferroelectricity provides a nice playground to play with, different types of free energy expressions. So in a real material, of course, we don't have just one-dimensional materials like the one I showed you. We need to take into account a three-dimensional displacement pattern of all the atoms. So, for example, barium titanate, what I show here is a prototypical ferroelectric where, say, the bariums are more or less stationary, but titanium and oxygens are displaced against each other to create this polarization. And this type of displacement is what you would call a Phonon displacement in undergraduate solid state physics. And the basic idea of these double well in a ferroelectric and a single well in a dielectric is also valid in this case in 3 dimensions, except that the horizontal axis now would not be just the polarization, but also this amplitude of this displacement, the amplitude of this Phonon mode. So in a ferroelectric, you would see this double well potential. Now, one of the early successes of DFT, and when I say early, I'm talking about early 1990s, so that says something about my age, I guess. But one of the early successes of DFT was to actually reproduce these double well potentials for the first time. So this is a Nature paper from 1992. This is something now a PhD student can learn how to do in a few months. In lead titanate and barium titanate, 2 well-studied ferroelectrics under different boundary conditions, Rancogne had shown this double well potential and showed that these first principles methods, these methods like DFT, which start from the Schrodinger equation without any fitting parameters to experiment, can really reproduce ferroelectric properties of materials. Now, what I had done in this field back in, this is last decade, 2011, was to study the ferroelectric properties of a new class of materials. So strontium titanate is a very well-studied perovskite. So it has this crystal structure with alternate strontium oxide and titanium dioxide layers. And one can imagine building other types of layered perovskites by adding a double SRO layer into the crystal structure. So this gives rise to the so-called Rhodes-Popper series with this chemical formula with different values of N. Now, we got into this problem right around the time that experimentalists figure out how to grow these types of structures for essentially any value of N that's not too large. And people were interested in whether these materials will become ferroelectric or not, what happens when you grow them on different substrates and so on. So without getting into the details, I just want to show you a comparison of the experimental results with the DFT results. So what we did on the theory part was to optimize the crystal structure by calculating the forces that are applied by the electrons on the atoms. You can find the point which gives rise to the zero force, so the minimum energy. And this is so the output is just the positions of the atoms, which is something you can also check with the experiment. So the 2 columns here are the scanning transmission electron microscopy data, where on the left you see individual atoms or columns of atoms, and the brighter ones are strontiums, and the less bright ones are the titaniums. Oxygens don't show up in this setting, but on the image on the right, in the bright field, BEF image, the darker spots you see are the oxygen positions. So this is really cool. Experimentals can really see the positions of these atoms, which still impresses me each time I look at a STEM picture. But what you cannot see with naked eye is that the center of these atomic unit cells, when you look at oxygens versus the cations, are shifted with respect to each other by a little bit. So if you consider the crystal structure here, where the red atoms are the oxygens, there are these quantities delta, delta x0, delta xc, etc., which are all non-zero. And what we did was we compared these quantities, so these positions of the atoms from Turan experiment. On the left, you see the position in the vertical direction. The black lines are the DFT results, and the data points with the error bars are the STM, the experimental results. And as you see, the match is pretty much perfect. I should say that whenever you see something that looks this good, you should be suspicious. And really what I'm showing you in this slide is the best result we got. Often the results are not as good, right? Here, there was some fortunate cancellation of errors as well. But nevertheless, the match is good enough to make us all happy. And in the in-plane direction, now the scale is smaller for the displacement, so the error bars are larger. But again, there is very good agreement between DFT and the experiment. So when it comes to things like crystal structures, the point I'm trying to make is, when it comes to things like crystal structures, density functional theory works surprisingly well, even with this local density approximation. And even in cases where you cannot actually capture the whole physics of what's going on in DFT, DFT can still tell you a lot about the properties of the system. For example, here is a very obscure compound with very few studies on it, so you don't need to know about this, obviously. And this sodium titanium chloride is a compound where you have these layers of titanium atoms, which form this so-called Kagome lattice. And each titanium has a spin 1 on it. And those spins interact with nearest neighbors antiferromagnetically. So it's a so-called frustrated spin compound. Interestingly, around 200 Kelvin, it undergoes a structural phase transition where these triangles you have, downward and upward triangles, change sizes so that you have alternating short bonds and long bonds. And this type of trimerization is due to what we claim to be a transition to a trimer simplex solid, which is a fancy quantum magnetic phase. It's a particular form of a valence bond solid, which I'm not really getting too much into here, unfortunately. But essentially, the exact diagonalization and DMRG studies before us was saying that, well, there's a trimerization order parameter between the nearest neighbor spins calculated over the up and down triangles, which becomes non-zero. Now, this is a quantum magnetic phase. This is not a phase that you can capture in DFT. So when I do a DFT calculation, this trimerization does not happen. However, what we can do is we can help other people actually do this quantum magnetism calculation. So there is a spin Hamiltonian. And even though DFT cannot solve this Hamiltonian, it can be used to extract the J parameters, the exchange parameters, with quite decent accuracy, and find the orders of magnitude of each one and the relative strength of each terms, and hence lead the way, or rather pave the way, for actual quantum magnetism studies. Okay, so this is all about what DFT can do. Now I will tell you what it cannot do. So in principle, it can do everything about the ground state of a system. It can predict everything, but there are two problems that breaks the Kohn-Sham and Hohenberg-Kohn expectations. One is the exchange correlation approximations, the local density approximation we are bound to use. And the other is that this Kohn-Sham approach actually relies on using non-interacting quasiparticles, gives you a single Slater determinant wave function. So it cannot capture any entanglement between its electron quasiparticles beyond what's required by the Pauli exclusion principle. So another way to look at this is the following. So this is a band structure. This is the typical plot that you see in first principles DFT papers, where on the horizontal axis you have momentum, or the wave vector k, the crystal momentum. And on the vertical axis, you have the energy. For each value of k, let's say at this point, there is an energy eigenstate here, another energy eigenstate here, another energy eigenstate here. Okay, so what this plot tells you, even though we don't talk about this explicitly, is that E of k is well defined. So for a value of k, there is a well-defined energy eigenstate. And this really means that K, momentum, is a good quantum number. Now, is momentum a good quantum number? If K is a good quantum number, then there must be translational symmetry. And indeed, in a crystal, there is discrete translational symmetry, but that translational symmetry is for the whole crystal, for all the electrons together. If you displace a single electron without leaving everything else in place by a lattice parameter A, then you can get a phase factor. So in principle, for single particles, there is no translational symmetry in an interacting system. And as a result, the band structure plot should not be like this. Instead, the best you can hope for is a plot like this, where you have these band-like features, sure, so there are some well-defined energies for K, but then these bands are fuzzy in the sense that these electrons have finite lifetime because they are interacting with everything else, and they are not, they are not going to stay in the same K state, a blob state, forever because of these interactions. So this is what you should expect, and DFT cannot quite give you. So what you need, and this is what, by the way, becomes important in correlated electronic systems. So in materials like, say, strontium vanadate, where there is an atom, vanadium atom here, with a partially filled d shell, a partially filled d orbital, the strong interaction on the same atom between the d electrons, and that becomes important in d orbitals for a particular reason, makes the electronic wave function become highly entangled, highly multi-determinant in the fermion language. And this is what we call electronic correlations, colloquially, and this is where DFT fails. So in order to approach a system like this, you need to switch to a Green's function formalism and introduce a complex self-energy, sigma here, where the real part will renormalize the DFT energies, E of K, and the imaginary part of this sigma will bring in a finite lifetime, will bring in the fuzziness in the plot. So the way that we do this is using the dynamical mean field theory approach in conjunction with DFT, so the DFT plus DMFT approach, where we take a single atom in the unit cell, vanadium atom in this case, and build an Anderson impurity model, where this vanadium atom is a quantum mechanical object that we treat at a higher level of theory.
Excuse me.
Oh, yes.
What is DMFT? What was it?
It's dynamical mean field theory.
Okay,
so,
thank you.
Yeah, it's a many-body computational approach, which we use in conjunction with DFT to study these correlated electronic systems. And it relies on using this so-called Anderson impurity model, which, okay, I don't have the Hamiltonian actually on my slide, so sorry for that, but it relies on singling out the transition metal ion, the ion that gives rise to strong correlations, and solving it more exactly with a better level of theory than DFT. So in practice, at the implementation level, this is how things work. So a DFT calculation, these are usually self-consistent calculations. So this is how you solve the numeric, differential equations. Involves this, so you get the wave function, you start with a guess for the wave function, you get the density from it, which gives you the Hamiltonian, solving the Hamiltonian gives you a new wave function, and you go over this loop until you reach self-consistency. In DMFT, we break into this loop and define a Green's function, which we use to define the hybridization of the vanadium ion with its surroundings, where everything else, so the strontium, the oxygen, the uncorrelated atoms, if you will, are treated at the level of DFT, like electron bath. And solving this hybridization gives us a self-energy. And then, of course, we do this whole thing, go over the whole loop until we reach self-consistency among everything. And,
last 3 minutes.
Oh, okay. I should really rush. Okay, thank you for that. So, this DMFT approach has been developed in order to study things like Hubbard model. So it was just a pure model approach. But in the recent years, technical developments in the last decade or so made it possible to use it in conjunction with DFT and use DFT plus DMFT in real systems like strontium vanadate. Okay, well, I have a sad face here because this little short arrow here takes about 3 orders of magnitude more computer time than everything else in this loop. But nowadays, it's not beyond the capability of modern computers. Okay, So this is what you get from DFT plus DMFT. So from DFT on the left and DFT plus DMFT on the right for strontium vanadate, this perovskite. So the band structure in DFT is well defined. There are these perfectly sharp bands, as I said, whereas in DMFT, there are two things that are different. One, there's a finite lifetime of these bands, so things become fuzzy. And if this was a more correlated material like a mott insulator, then you wouldn't even see the bands, you would just see a cloud of electronic states. But the other thing that's different is the width of these bands are different. In DMFT, you end up with bands that are just about half as wide as they are in DFT in this particular system. The ratio we denote by Z, this is the quasi-particle residue. And when you compare this with the experiment, two things are apparent. One, okay, if you are an expert in this field, I guess I should say that the Fermi liquid approach is still valid because the imaginary part of the self-energy goes to zero right at the Fermi level. So right at the Fermi level, things are perfectly sharp. But when you compare with the experiment like ARPES, angular result photoemission, photoelectron experiment, then the bandwidth of DMFT matches much better than that of DFT. So here the green line is DFT. This is from an earlier work of someone else, whereas the background is ARPES, what you see in the experiment. And as you see, the ARPES data is just half as wide as the what DFT predicts, so in line with the DMFT. Now, the reason that this happens is that the effective mass, which is related to the inverse second curvature of the band energies in DFT, which I denote as M band, is different from what you get in DMFT by a factor of Z. This Z is the quasi-particle weight or quasi-particle residue, and you can expand it to first order in terms of the self-energy, electronic self-energy, which is by definition zero in DFT. So we find a Z of 0.55, so we find wider band, narrower bands. So electrons behave just like twice as heavy in DMFT compared to DFT. I'm almost over time, but this is my last slide, I promise. So you might say that, well, this is just a simple quantitative correction in the case of strontium vanadate, but it turns out that this makes a big difference for a particular application. Now, the plasma frequency of metals, so this is the frequency of the collective oscillations of electrons, is very important for optical properties because up to the plasma frequency, metals reflect all electromagnetic radiation that's incident on them. So the reason that aluminum looks like gray and reflects all the light that you shine on it is that it has a plasma frequency well above the visible spectrum. Now, if you believe DFT, the plasma frequency of strontium vanadate is 1.7 electron volts. So it should be a red solid. It should reflect all red light. But if you take into account this Z, this quasi-particle weight as well, since the electrons behave more heavily, this plasma frequency goes down. It becomes harder to oscillate them. And the plasma frequency is suppressed to 1.2 EVs, which makes it a transparent metal. So it reflects infrared light, but not visible light. And it turns out that these transparent conductors are very exciting for engineers. So you can see, electrical engineers mouth water when you talk about a transparent metal, because for various applications, we need good conductors of electricity that are also transparent to visible light. And experiments really confirm this prediction that the plasma edge of strontium vanadate is at around 1.2, 1.3 EV, and you can really see through it to a great extent. And what you see here is the substrate. You don't even see the film on typical screens. Okay, I guess I'm over time, so this is where I'm going to leave you with my summary. If you're interested in these types of calculations, these types of methods, there are many different review articles out there, but we have a recent one that was really aimed at non-experts in the field, so I'm leaving the reference here. Oh, okay, this is the wrong reference, but there's another paper that cites this one, so you can email me and I can send you the reference. Okay, thank you very much for your attention.
Actually, we thank you very much, Turan Hocam. If there's not any question from the audience, I would like to kindly ask a question. And it
Sure.
seems that no question.
I have a question, if I may.
Okay, please.
Yeah, thank you for the talk. In quantum computing community, especially over the last years or so, there has been a lot of work on using tensor networks to sort of solve these many-body problems. Can you comment on the relative strengths of those and weaknesses compared to density functional theory?
Sure. I guess the main difference is the following. There are many methods which solve the problems, say, if you want to work on Hubbard model at the model level, in that, and DMFT was there, say, about 20 years ago too. So I give you a Hamiltonian with, say, 3 parameters, and people try to solve it. The strength of DFT plus DMFT now is DMFT has been interfaced with DFT to work on actual materials. So when I do a calculation, I don't say, well, I have a Hubbard model with this many orbitals with, these parameters. Instead, I say, these are the atoms I have, this is the crystal structure I have, and the result I get is a result for that specific material. As far as I understand, things like tensor networks did not make it to this stage yet, so they are not first principles. But I'm pretty sure, given enough time, like in 10 years or so, they will reach there too. So in the models, DMFT, dynamical mean field theory, captures everything that is local to a site. So that's local in space. And it's relatively cheap compared to these other approaches. But things like tensor networks are better in capturing non-local correlations. So in a way, depending on the problem, each method, even just at the model level, have their own strengths, and computational cost being one of them.
Thank you.
Thank you.
Actually, I have a question. Okay, I will behave like a doctor, and I will ask if I can, how to say, heal my patients using this, the new version of this DFT. Okay. Will I be able to calculate entanglement using this approach between, for example, electrons, or maybe some other things?
Yeah, so some other things is tough. So in all the calculations I did, atoms are classical objects. They stay where they are happily, so they are not even vibrating. If you are interested in things like the electron phonon coupling, so or entanglement between them, one needs to modify these approaches. In terms of the electron entanglement, sure, but there is okay, I shouldn't comment too much because I'm not quite an expert on those, but how entanglement works in solids, in these many-body systems and so on, is actually tough. Like the definitions are, well, this is a quantum optics conference, so I'm sure there are people who are more experts on this. How you approach it and how you define entanglement, etc., is up to debate. But essentially, what I can give you is the self-energy. Now, this self-energy, of course, doesn't directly tell you what the entanglement is, but it tells you a lot about various other properties like these finite lifetimes and so on when you look at a single electron excitation that arise from the entanglement. So in other words, another way to, I guess, answer this question is I can give you a 1 electron density matrix. Now, that density matrix does tell you something about the presence or absence of entanglements, but it doesn't tell you everything about it, right? Because it's the 1 electron density matrix.
Okay, there's another question. This is the last question I can take. DFT has problems. This question is from Professor Sadi Turgut. Okay, there is one. Okay, DFT has problems with miscalculating semiconductor band gaps, I believe. Would DMFT be able to solve this problem as well?
That's a great question. And the short answer is no, because the semiconductor band gaps are underestimated due to things like more like long-range exchange, etc., that is not added in the type of DMFT that I'm using. In transition metals, the multi-insulating phases are often predicted to be metals by DFT. So DMFT can correct that because that is due to the local physics on a single transition atom. But the semiconductor band gap problem would not be solved by DMFT. There are other approaches like GW or more HSE and so on, where people try to correct those band gaps. But DMFT would be the wrong tool for that.
I told last question, but there's another interesting question, so I would like to read it. This is coming from Professor Özgür Müstecaplıoğlu. He's from Koç University. To which extent we can tune the transparency and its bandwidth, say by using external fields to generate strain on the bonds to tune their lengths?
That's a great question. So we spent more than a year, and that's actually the main point of this wrong reference I cite in the end, trying to do exactly that. It turns out that in strontium vanadate, due to, in a way, simplicity of the cubic crystal structure, strain does nothing. So strain, pressure, etc., doesn't change the plasma frequency, and transparency as a result at all. Like, just negligible changes happen only. But we are still looking for other materials, perhaps layered materials or materials which have more complicated crystal structures, which would be more sensitive to strain, to do exactly that, to actually tune the optical properties using strain and other external knobs that we can use in the laboratory. So
thank you.
Yeah,
our time is
in a couple of years.
Thank you very much. Thank you very much for your beautiful presentation, and I also thank the audience for the questions.